Welcome to this explainer. Have you ever actually stopped to wonder about the sheer invisible power holding our physical world together? The solid ground beneath your feet, the literal salt on your table, it's all locked together by these immense hidden forces. Well, today we are diving right into a topic that sits at the very heart of thermodynamics to map out those unseen forces, and it's called lattice energy. We're going to go on a bit of a journey today. We'll start with perfectly mathematical spherical ions and move all the way into the somewhat messy, distorted realities of actual chemical bonds. If you've ever looked at a complex energy cycle and thought, what on earth is going on with all these arrows, you aren't in exactly the right place. Let's get started.
Here is our roadmap for today's explainer. We've got 1. Defining lattice energy. 2. The rules of attraction. 3. Decoding Born-Haber cycles. 4. Theory versus reality. And we'll wrap up with 5. Avoiding common mistakes.
Okay, Section 1. Defining lattice energy. To really wrap our heads around ionic bonds, we first need to establish our ground rules. Now, the specific wording of this definition is actually fascinating, especially when you think about the physics at play. Lattice energy is the enthalpy change when 1 mole of an ionic solid is formed from its gaseous ions under standard conditions. Picture it. You have these positive and negative gases floating freely, completely isolated. Then, suddenly, they slam together to form a highly structured solid lattice. Because these gaseous ions are coming together and their potential energy is dropping sharply as that attraction takes over, this process naturally releases energy to the surroundings. Therefore, lattice formation is inherently an exothermic process. The energy value is basically always negative.
And this specific number brilliantly illustrates the sheer scale of that energy release. Just forming 1 single mole of standard table salt, sodium chloride, from its gaseous sodium and chloride ions releases a massive 787 kilojoules of energy. That is a seriously highly exothermic reaction right there. Moving right along to Section 2, the rules of attraction. What exactly governs these invisible electrostatic forces? Ultimately, lattice energy is governed by Coulomb's law, which basically tells us that the electrostatic attraction between ions depends heavily on their charge. Take sodium chloride, for instance. It's made of Na+ and Cl- ions, so that's a +1 and a -1 charge. Now, compare that to magnesium oxide, which is made of Mg2+ and O2- ions, a +2 and a -2 charge. Because the ionic charges in magnesium oxide are double those in sodium chloride, the electrostatic attraction gripping them together is going to be significantly, noticeably greater.
And the result? It's honestly staggering. While sodium chloride releases that 787 kilojoules per mole, magnesium oxide releases 3,795 kilojoules per mole. That is just a huge, dramatic increase in energy released, entirely because we stepped up from single to double charges. So the crucial takeaway here is that 2 main factors dictate this energy. First, as we just saw, a higher ionic charge means stronger attraction. But second, a smaller ionic radius also plays a massive role. Think about it. If you have a smaller ion, like lithium compared to sodium, the nuclei of the bonding atoms are physically capable of sitting much closer together. Less distance means stronger electrostatic attraction, and that translates directly to a more negative, larger lattice energy. High charges plus small ions, you're going to get massive lattice energies.
But here's the catch. We actually can't measure this lattice energy directly in a lab. So how do we figure out these numbers? That brings us to Section 3, decoding Born-Haber cycles. Think of this as our chemical energy bank account.
The Born-Haber cycle relies perfectly on Hess's law. If you remember, Hess's law states that the total enthalpy change of a reaction is independent of the route taken. So if we know the total standard enthalpy of formation, that's the energy change when making a compound from its raw elements in their standard states, we can essentially set up a mathematical equation. By rearranging it, we can isolate the lattice energy simply by subtracting all the other steps from that enthalpy of formation.
Let's walk through this process for sodium chloride. Treat this like an accounting ledger, though, thankfully, chemical bookkeeping is much more explosive than doing your taxes. Step 1, we atomize the solid sodium into a gas, which means spending energy. Step 2, we ionize that gaseous sodium, ripping away an electron. Step 3, we atomize the chlorine gas, literally breaking the Cl2 molecule apart. Step 4, we give that loose electron to the chlorine atom. This is the electron affinity, which actually pays some energy back to us. And finally, step 5, those 2 gaseous ions snap together in lattice formation. If we have the energy values for steps 1 through 4, and we know the overall formation energy, we can easily find step 5.
Now, pay close attention, because this is where the most common trip-ups happen, the mathematical signs. You absolutely must distinguish between endothermic and exothermic processes. Atomization and ionization, they require us to break bonds or overcome attraction, meaning we have to spend energy. Those are positive values. But the first electron affinity and lattice formation involve things coming together and stabilizing, releasing energy to the surroundings. So, those are negative values.
But I want to throw a quick speed bump question at you. We literally just established that electron affinity is negative, right? So why, when we are forming a specific ion, like oxygen 2-, is the second electron affinity suddenly a positive value? Why do we have to start paying energy in?
The answer comes down to pure physics. When you add that first electron to a neutral oxygen atom, it happily releases energy. But now, you've got an O- ion. If you try to force a second negative electron into an already negative electron cloud, they are going to inherently repel each other. To overcome that strong electrostatic repulsion, you have to actively supply energy to the system. Hence, the second electron affinity is always going to be positive.
Okay, we've done our math. Now we arrive at section 4, theory versus reality. Because let's face it, real-world chemical bonds can get a little messy. We essentially have two types of lattice energy floating around here. You've got theoretical lattice energy, which is what we calculate using pure physics and Coulomb's law, assuming our ions are perfectly round spheres and the bond is 100% ionic. Then you've got experimental lattice energy, which is what we derive from our Born-Haber cycle based on real-world measurements. If these two numbers match up closely, great, the bond is mostly ionic. But if these numbers differ greatly, well, it indicates our supposed perfect ionic bond is actually harboring a covalent secret.
That discrepancy is caused by a phenomenon called polarization. Polarization happens when a highly charged positive ion physically pulls on and distorts the electron cloud of a neighboring negative ion. Instead of perfect spheres sitting side by side, the negative cloud gets stretched towards the positive ion. This sharing of electrons actually introduces covalent character right into the ionic bond. And because of this extra sharing, the bond is physically stronger than the pure ionic theory predicts, which makes the experimental lattice energy much more negative than our theoretical calculations.
And we can predict exactly when this is going to happen using Fajon's rules. High covalent character in an ionic compound occurs when you have a small, highly charged cation, like aluminum 3+, paired with a large, squishy anion, like an iodide ion. Because aluminum has a +3 charge and is very small, it has massive polarizing power. It heavily distorts that large anion. This is exactly why a compound like aluminum chloride is significantly more covalent than a compound like sodium chloride.
All right, let's move to section 5, avoiding common mistakes. I want to give you some immediate, practical value for when you are running these calculations yourself.
So, here are the most common accounting errors you need to watch out for. First, forgetting that lattice formation must be a negative value. Second, if you're working with a group 2 metal like magnesium, you absolutely must remember to add both the first and the second ionization energies. Third, like we discussed, don't forget the second electron affinity for oxygen, and remember its sign is positive. And finally, for halogens like chlorine gas, if they give you the bond dissociation energy, you have to halve it to get the atomization energy for a single atom. Keep an eye out for those.
And that brings us to the end of our journey through lattice energy. We've seen how to calculate it, what physically drives it, and how to spot errors. But I want to leave you with a bit of a provocative thought as you look at chemical equations going forward. Whenever you see a simple, straightforward ionic formula, ask yourself, is your perfectly calculated ionic bond actually hiding a messy, polarized, covalent reality? Keep questioning what's beneath the surface. Thanks so much for joining me on this explainer, and keep learning.